Okay, thank you very much for your nice introduction. This presentation is originally from a resident research session. After doing some updating, I'm presenting today for our tech talk. Today, I'm going to talk about the basic concepts related to multivariate statistics, framework of multivariate statistics. First, talk about multivariate regression analysis. And then I will talk about the framework of structure analysis, focus on factor analysis, and we'll give some ideas about the structure equation modeling. In statistics, we often can hear some concepts like univariate, bivariate, and multivariate statistics. What's the difference? Generally speaking, when we say univariate statistics, we only summarize one variable at a time. Univariate analysis refers to the analysis of one variable, which is the simplest form of data analysis. Data being analyzed contains only one variable. When we see the bivariate statistics, we try to compare two variables. Bivariate analysis is used to find out if there is some relationship between two different variables for the purpose of determining the empirical relationship between the two variables. Multivariate statistics is quite different from univariate and bivariate, which is compare more than two variables. Multivariate analysis is the analysis of three or more variables. On the other hand, we can see multivariate and multivariable statistics. Those are also quite different. When we say multivariable, usually we mean multiple variables. This analysis refers to a statistical model in which there are multiple independent variables. And usually when we say the multivariable, we only have one outcome. But multivariate analysis refers to a statistics in which we have two or more dependent or outcomes variables. So when we say multivariate, it means we have two or more variables as outcomes. A multivariable model can be sort of a model in which multiple variables are found on the right side of the model equation. This type of statistical model can be used to attempt to assess the relationship between a number of variables. We can assess independent relationship when adjusting for potential confounders. But the multivariate statistics with two or more outcomes. So the multivariate statistics is a subdivision of statistics encompassing the simultaneous observation and analysis of more than one outcome variables, which means multivariate statistics concerns understanding the different aims and the background of each of the different forms of multivariate analysis and how they're related to each other. The practical application of multivariate statistics to a particular problem may involve several types of univariate and multivariate analysis in order to understand the relationship between variables and their relevance to the problem being studied. Multivariate statistical analysis is concerned with data that consists of set of measurements on a number of individuals or subjects. The sample data may be like height or weight of some individual drawn randomly from a population of school children in a given city. Here, our outcomes consist of height and weight. Or the statistical treatment may be made on a collection of measurements such as length, width, and others. And all study the scores on batteries of mental tests administered to a number of students. In medical research, the multivariate statistics are often related to quality of life measurements, as we can see later. So when we talk about multivariate statistics, we have like more complicated notation compared to univariate, bivariate, or even multivariable statistics. So we have P denote the number of sets or measurements on given individuals, and we have the sample size M. Univariate statistic is concerned with the random scalar variable Y. So which means Y is just scalar, which means just the one outcome. In multivariate analysis, we are concerned with the joint analysis of multiple dependent variables. Those variables can be represented using matrices or vectors. This provides simplification of notation and form for exploring important formulas. So for example, suppose we have two outcomes, height, left arm length, and the left foot length for participants in a study of physical characteristics of adult humans. So our outcomes will consist of height, left forearm length, and the left foot length. So that for each participant, our outcome will consist of 3 measurements. And then for one participant, we can have the outcome Y1. And for the second individual, we can have the outcome for the Y2. And for the third individual, the person will have height, forearm length, and foot length Y3. So the outcome in matrix will follow in a 3x3 matrix. So this is one of the important difference between the multivariate statistics and other statistics. And then we can indicate like for the matrix, use the vector and use the matrix notation to indicate the outcomes. Another example, like in our cardiovascular studies, we have SBP, DBP, and we have the outcome consists of 2 variables, SBP and DBP. We can have the outcome Y as a matrix. In the matrix, we just solve with Y. The first column gives the data for SBP, and the second column gives the data for DBP. Each row gives data for a patient in the sample. To repeat the rows are observations and comments on the outcomes SBP and DBP. If we would like to visualize our multivariate analysis for the outcomes, we can use like the scatter plot provide us the outcomes. Based upon the visualization, we can say that for the outcomes with multiple variables, we can see not only the single outcomes descriptive statistics. One more important thing is about the relationship among these outcome variables. So this is the reason we can say the visualization for the multivariate analysis. Mathematically, suppose we have n independent subjects with p number of sets of measurements on a given individuals. So we can indicate the outcome in a matrix Y is the matrix n times p data matrix, and then for the p outcomes, and then with n subjects. Instead of using the normal distribution for one outcome, for the multivariate normal distribution, we will provide a multivariate normal distribution. So we can see the probability density function for the multivariate normal distribution. And here we have the random vector, we have the multivariate normal distribution, mean vector, covariance matrix, and the dimension of a random vector. So multivariate analysis can be represented by a function use yn times m related to design matrix and the coefficient matrix and the error term. This is like the extension of regular linear regression. Instead of just use a vector for one outcome, we have a matrix for the response matrix. What is the difference between multivariate analysis and standard linear regression? In standard linear regression, we have a scalar response variable y and the vector of design matrix. The focus of interest is on how knowledge of like the covariance X influence distribution of Y, the mean of Y. In contrast, the multivariate analysis, the focus is a vector Y in which all the components of Y are viewed as a response rather than covariance, possibly with additional covariant information matrix. So we will require the normal and the general multivariate model and distribution theory. The study measurements of relations, probability computation of multidimensional regions, and the explanation of data structure and the patterns. The multivariate linear regression is represented by this equation with matrix. And we can use the linear model function in R or other software, while the left side is the model consists of a matrix of response variable, and the right side, as usual, is the design matrix as for a univariate. And we can use like ANOVA and others. But more important, the new thing is about the multi MANOVA for the analysis. And later we will use an example to show how can we use the MANOVA to explore the relationship. Many different models are used in the multivariate analysis, each with its own types of analysis. Quite often is multivariate analysis of variance. This is called the MANOVA. It's the extension from an ANOVA. It extends the analysis of variance to cover cases where there is more than one independent variable to be analyzed simultaneously. Multivariate regression attempts to determine a formula that can describe how elements in a vector of variable respond simultaneously to change in others. For linear relations, regression analysis here are based upon form of the general linear model. There are many types of multivariate analysis. One is called the principal component analysis. Last month, Kashiba gave us a wonderful talk about PCA, principal component analysis, which creates a new set of orthogonal variables that contain the same information as the original set. It retains the axis of variation to give a new set of orthogonal axes ordered so that they can summarize describe proportion of the variation. In recent decades, in addition to the principal component analysis, another very popular and important analysis related to factor analysis is similar to principal components, but allow us to extract a specified number of variables fewer than the original set and leaving the remaining unexplained variation as error. The extracted variables are known as the latent variables or factors. Each one may be supposed to account for correlation in a group of observed variables. There are many types of factor analysis. Multivariate regression is a technique that estimates a single regression model with multiple outcomes variables and one or more predictor variables. We can collect the data on 3 psychological variables, for example, 4 academic variables or like a quality of life. And we can see the psychological variables, mental health, and others. We are interested in how many dimensions are necessary to understand the association related to these variables. First, let's look at like a theoretical variables, like the psychological variable and related to lots of control, self-concept, and motivation. And also we have some other independent variables. So when we conduct a multivariate regression analysis, many statistical software can conduct this analysis. The first I would like to recommend for using CES, because compared to other software, CES can use a very simple syntax to generate very comprehensive outcomes. So the syntax for estimating a multivariate regression is similar to running a model with a single outcome. The primary difference is that uses the MANOVA statement so that the output includes the multivariate statistics. They also have like multivariate criterion for tests, like this F statistics and the corresponding p-value. By specifying the MANOVA statement, we indicate we would like a multivariate statistics for all of the predictor variables in the model. So by using the very simple CES code, like GLM, we can say it's like to handle continuous variable for the independent variable. The only difference for the model is that we can put all of the outcomes, dependent variables, on the model's left side, and we can put the risk factors or independent variable on the right side, and we just use the MANOVA, we can generate the results. Now I'm going to talk about a data set I played with for many years in our healthcare. This is the measurement of disease-specific health data. The data set comes from a clinical trial, I think now it's about 20 years ago, related to angina. We have one of the important tests in this study is about quality of life. We use a Seattle angina questionnaire to measure the quality of life. Health data related to angina assessed directly from patients at a baseline, 1 month, 3 months, 6 months, and each year by the annual evaluation. We use the Seattle angina questionnaire to measure the quality of life. Seattle angina questionnaire consists of the 5 domains: physical limitations. In our data set, later we will use SQ1, angina stability, SQ2, angina frequency, SQ3, treatment satisfaction, SQ4, and the quality of life. So in this study, we have 5 quality of life scores as outcomes. So our outcomes consists of 5 variables. Also, we have another overall general health data. Later we will see we have 8 domains of outcomes. So coming together, we have 13 variables for outcomes. And we can use this very simple CES code to put all of 5 domains of outcomes in the model. And then we put the risk factors as predicted variables, like treatment, like age, like diabetes status, like gender, like MI, and also like race. And here we put the MANOVA, they will generate all of the results. So first we can see, since the 5 domains are correlated, so we will see if we consider 5 domains simultaneous, we will look at the effect of treatment. So this is the results. We can see overall, the treatment can have a significant impact on the quality of life for each domain. Also, 5 domains. For each domain, we can run ANOVA analysis. So we will see for the dependent variable for SQ1, and we have the results of SQ2. So if we run the 5 domains, we will get the 5 ANOVA. But remember, if we run the separate 5 domains for the analysis, the problem is that we will ignore the correlation or the covariance among each domain. So since the 5 domains are highly correlated, so it is necessary for us to test for the overall effects of treatment and other variables like for the age and others. So this is the reason why if we only conduct 5 separate ANOVA analysis, it's not necessary to capture the overall results for this 5 domains outcome. So this is the reason why we need to like the ANOVA here, and also we have the MANOVA for the overall age effects and other variables. If we use other software like R to run, and of course we can get the corresponding information, but instead of like use very simple or even single line command to get the all of the ANOVA results and the MANOVA results, we need to specify the code in R first. We need to go like use LM function, use the same band the command to put all of the outcome together and then to run the model. If we would like to get the multi MANOVA results, this outcome just use LM will not generate it automatically, but we need to use another order like VCOV for the model to generate the MANOVA. As I just mentioned, separate ANOVA are not equivalent to the results from MANOVA because we need to determine whether or not to include the predictors in a multivariate regression. So we need to conduct the multivariate test statistics. Often we can use it. When we use the multivariate reference to the multiple response or dependent variable, that means we use modified hypothesis tests to determine whether a predictor contributes to a model. That covariance needs to be taken into account when determining if a predictor is jointly contributing to both models. For example, the effect of some variables maybe just for some borderline, they appear significant for one outcome, but not for another outcome. So it's not enough to just look at the one NOVA separately. So we need to formally test for their covariance. So this is the reason we need to test involves the covariance between the coefficients in both models. So this is the very simplest way for us to run multivariate analysis by using just the multivariate multiple regression. In recent decades, when we dealing with the situation with multiple outcomes or responses, we often use factor analysis. One of the techniques is about the structure equation modeling. Structure equation modeling represents the hypothesis the pattern of relations among a set of observed variables. The purpose is to provide a meaningful and parsimonious explanation of observed relations. There are many different types of analysis to look at the multiple outcomes and also with many independent variables. We can do like the path models, the model relations among observed variables. We can conduct like the path analysis. We can use like the measurement models, model relations between observed and latent variables. And also structure models. There's a model relation among latent variables. So here we have many new concepts related to multivariate analysis. Traditionally, we use the we use like this analysis, such as like a factor analysis, for example, like the principal component analysis, simultaneous equation modeling, evaluation of relationships among latent variables by combining the strings of factor analysis and the multiple regression in a single model can be tested as statistic. Simultaneously assessment of multiple dependent variables and both direct and indirect of variables on another. We can generate some indices of overall fit or hypothesis model to the data, and then we can flexible in feeding alternative models. I'm going to use a data set from our previous studies from Courage and others to see. This Courage project is about the PCI to the optimal medical therapy in reduce the risk of cardiovascular events. So our treatments will be PCI plus optimal medical therapy versus optimal therapy alone. For the multivariate analysis, we working on the quality of life data in Courage. As I just mentioned, we used the Seattle questionnaire, is called SEC, to measure the disease-specific, Angela-specific quality of life. And also we use the random statistics for the overall medical related quality of life. We already talked about the Seattle Angela questionnaire for the quality of life. We have the random statistics consists of 8 domains for the quality of life. We have physical functioning, role limitation physical, role limitation emotional, energy fatigue, emotional well-being, social functioning, pain, and general health. So coming together, we have 13 variables to indicate quality of life. And then we can combine these 2 instruments together to measure the quality of life. So we have Angela health status as the outcome. We have the random statistics for general health status as outcome. And also we have many independent variables. So we would like to use multivariate analysis to capture the quality of life. So here, as we can see, we have Y, like before, as the outcome or dependent variable. And we have X as the independent variable. So in multivariate statistical analysis, we use X, like the P times 1 vector of measured endogenous variables, which means the independent variables. We have Y equals Q1 vector of measured exogenous variables. And then we have the vector of exogenous factor and the vector of endogenous factor, and lambda. The model parameters can be divided into 2 groups: measurement model parameters and the structure model parameters. So here, since we use like the observed and the unobserved, so we will have the latent versus observed variables. Observed or manifest variables are the measured variables in the data. They may or may not be viewed as a good indicator of more fundamental latent variables. A latent variable is a variable cannot be directly observed or measured, but is assumed to exist based upon observed or measured measurable data. For example, we can have a latent variable called the angina-related health. Another is called the overall health. That can be considered like the latent variable. It's often referred as the hidden variable and is typically inferred or estimated by analyzing patterns or relationships among observed variables. They must be related in some ways to one or more observed variables. For example, for the disease-related health status measured by the 5 domain for Seattle angina questionnaire. And then we can have like the passive analysis, we have the observed variable. Like here, we have like the treatment, age, gender, and others. We have a latent variable. Okay? This is the latent variable. And here, we have the lambda and psi as the latent variable. We can look at the relationship between the independent variable to outcomes. And also, this relationship may be like directional or non-directional. So we can explore the different relationship between the independent variable and the outcomes based upon our analysis. So for example, we have the outcome Y1 and Y2. So for example, maybe the Y1 is angina-related healthcare, and the Y2 is the overall, and the X are the independent or exogenous variable, while the endogenous variable, which is the dependent on outcomes. And then the outcomes could be related. For example, like the angina-related disease can be contribute to the overall health status. And we have this path coefficient from an independent variable to outcomes, also from one outcome to another. And more importantly, we need to consider the common factor variance or covariance or the dependent or exogenous variables. So we will consider the covariance among outcomes. So we can have like this matrix and use the equations to describe this relationship. And also, we could have another relationship. We have like the different set of independent variables. And the outcomes, we have 3 groups. So for example, we have like angina, health related, we have overall, and also we may have like this like a mental health. So we could have like this relationship. And then we can get this measurement model for exogenous or independent variable for the endogenous variable. After the measurement model, we could have the construction model, which related to the structure, which means related to latent variables. So this is the relationship like before. We have this latent variable for outcomes and for the independent variables. They also could build up the relationship. So we will have a structure model matrices. So in our healthcare, we could have like the clinical outcomes, like SBP, DBP. We have behavior outcomes. And also we could have like the lifestyle or as independent variables. So we could build up this direct relationship among the constructors. And then for these constructors, we could build up our measurement model equation, and then we consider independent variables and outcomes variables. And outcomes variables, a group of outcome variables can contribute to another group of outcomes, and then we can build up the measurement model equation for independent variable and also for outcomes variable. And then if like we have 16 or even more outcomes or the independent variables, we can build up these equations. And we build up the equations for the independent variable, and then we build up the equations, measurement equations and the structure equations for the outcomes. And then we can specify by using like this different type. For example, if we would like to measure the general intelligence, we can use the 4 different risk factors like the verbal capacity, spatial capacity, math capacity, and net capacity. Okay, so this is the basic way for us to conduct. When we conduct this structure analysis, we use the covariance matrix to reflect the relationship. Generally speaking, we recommend to use covariance matrix instead of correlation matrix. So we will have the observed covariance matrix, and then after run some model, we have the model implied covariance matrix. After that, like in the ordinary regression, we will get a residual matrix. This residual matrix is the observed covariance matrix minus the model implied covariance matrix. And then we can summarize the magnitude of residual matrix. So this is like the basic mechanism. So for the outcomes, we will figure out the covariance matrix. When we try to analyze the model, this is the basic way for us to do for the model estimation. First, we attempt to estimate model parameters. We produce the covariance matrix based upon the estimate model parameters, which is the model implied covariance matrix. And then we compare model implied covariance matrix with observed covariance matrix, and then we get the residual matrix. We minimize the residual matrix through a series of attempts, and then generate a number and summarize the magnitude of residual matrix, which is the fitting function. When we say a model is to be fitted to observed model, which means the implied covariance matrix is equivalent to the observed equivalence. So we will get the close approximation to the model. An optimal outcome is a model that fits the data closely and yield a highly impressible solution. Models that are at their best can be expected to provide only close approximation to observed model rather than the exact fit. So this is like our ordinary studies. So we can use several types of criterion. The common use is for the chi-square test, but this chi-square test is highly related to the sample size. So there's chi-square test reject the model quite often. We could use like absolute fit indices, like RMSEA or SRMA. Use this absolute fit indices, we can access the degree to which the model implied covariance matrix match the observed covariance matrix. And then we can gauge for the badness of fit. When we look at the RMSEA or SRMA, the smaller the value, the better the model fit. Usually, 0 means the optimal fit. Increased value indicate a greater departure of implied the covariance matrix from the observed matrix. And also we can use other indices like incremental fit indices and others. So this is the way for us to get a standardized root mean square residual. So usually we recommend for 0.08 as a cutoff point for the adequate fit. This is the way for the incremental fit for the CFI. For the CFI, should like greater than 0.95 for the adequate fit. Now, see, we can see like for the confirmatory factor analysis for the physical health and the mental health, and also we can use this fit for the clinical improvement in physical limitation. So this is the way for the model. We use the intercept, slope, and often other latent variables for the longitudinal analysis with this sense. This is another example to show like how can we use multivariate analysis for like the 8 outcomes, use some dependent variables, 3 dependent variables to measure these outcomes. As we can see, with the different outcomes, we will see the latent variable. One is called the DE-CTR, another called the DE-CTR. So that's as the quality of life for these outcomes, and that's related to the baseline independent variables. So this is the way for us to generate the results. And then for this structure, we can have this like the measurement model. As we can see, for the 3 latent variables, DE-CTR, IND-60, and DE-65, we can specify the measurement model. So first, we define the measurement model. As we can see, for the latent variables, for the IND-60, this is related to 3 independent variables. So this is the reason why we have IND-60 is the function of independent variable x1, x2, and x3. For DE-CTR, that's related to 4 outcomes, y1, y2, y3, and y4. So this is for DE-CTR. And then for the DE-65 related to outcomes y5, y6, y7, and y8. And then we can see the relationship. This is the structure. Like I say, DE-CTR is regress on IND-60. And DE-65 is regress on IND-60 and DE-60. So this is the reason we get this regression model. For the residual correlations, we get this relationship. So this is a structure equation model for this structure, which means when we use this structure equation modeling, we can explore this complicated relationship by using like the measurement model, regression, and also we will see the residual correlations. So this is the structure equation model, how can we use this way to get the equation? And we can use after run the analysis, we can get the based upon the observed covariance matrix, and then we can get like the noding for each component. And here we can see the node for each outcome from y1, y2, y3, y4 to y12. The magnitude for this each outcomes indicate the weight or the importance for the latent variable, and then also we can see the relationship between the latent variables. That will provides us the idea about how important these dependent variables related to the latent variables. And then we can get this output for the test statistics, and we can get the model evaluation information, like use the model versus the baseline model. We can get the CFI and the TLI and other variables. And also we can get the RMSEA for this model connect. And also we can get the latent variables. This is from another example to show how we can get this covariance and correlations to show the results. The basic important thing is to figure out this structure for the model, and then to specify this measurement model, and then we get this observed covariance matrix. So this is the reason why when we use the structure equation modeling, we can successfully capture the relationship among those variables, and then we get the results. So in summary, when we conduct the analysis related to multivariate statistical analysis, we can better understand the different aims and the background of each of the different forms of multivariate analysis. Multivariate analysis are used reason to see the patterns of data, to make a clear comparison, to discard unwanted information, and to start multiple factors at once. Multivariate analysis takes the whole host of variables into consideration. That makes it complicated as well as essential tool. So in recent decades, there are many different ways for us to conduct this multivariate analysis. Generally speaking, multivariate regression analysis can be considered like straightforward and comparatively simple. But for other analysis, they need some specific way and tools to understand this structure and to conduct the analysis. So there are some specific software like M+ and others for us to run multivariate statistics. One of the important things for multivariate statistics is that as many factors into consideration as possible, which means we could have the pretty complicated relationship among the outcomes variable and the independent variable. And also we can consider the different relationship. So this results can like tremendous reduction of bias and give us results closer to the reality. So this is the reason the multivariate statistics in recent years has been have been developed very quickly. And also several R-related packages have been developed for us to conduct multivariate statistics. Okay, that is the material I would like to present today. Questions, comments?
Thank you, Zugui. Any questions from the audience? All right, well, I have a couple of questions.
Yeah, sure.
We often do multinomial analysis. Is this a subcategory of the multivariate? Multinomial.
Oh, multinomial is different from the multivariate. Multinomial usually refers to the outcomes with 3 or more levels. The outcome is just one. The outcome is just one. For example, we have diabetes, and we can classify it as normal, pre-diabetes, and diabetes.
I see.
Yeah.
I see.
Yeah.
Like, okay. So it's one variable which can be ordinal or ordered in some ways, and but it's only one variable instead of multiple variables.
Yeah. Usually in logistic regression, we only have two levels, yes or no. But multinomial means 3 or more levels.
I see. In one of the, I think in one of the SAS outputs that you showed, I couldn't figure out. You were looking at the effect of the treatment, but where do you see the effect of the treatment? Yeah, I guess that's this one.
Okay. Here, this treatment say overall, if we look at the MANOVA test criteria, the overall RX means the treatment effects. Overall.
So where do you see that? I'm sorry, go ahead.
So if you look at the second part, MANOVA test criterion and exact F statistics for hypothesis of not overall RX effect. Yeah. So this is the overall significant.
And so which one would you, I mean, I don't know anything about Wilks lambda, Pillay trace, Hotelling-Lowley trace, Royce-Ritter's rule. Which one do you choose to say that it is overall significant?
Usually, I prefer to choose the first one, Wilks lambda, which means the overall the treatment effects is significant for 5 domains. But the most important thing is that if we conduct like 1 by 1, there will be not this case. So this is the reason. When, like I said, like for dependent SQ1, SQ2, so this is not enough for the independent for separate. So this is the example I provided. So for example, the covariance needs to be taken into account. The could be for one outcome is significant, but for another one is not significant. This is quite often. So for example, for the angular severity is significant, but for the treatment satisfaction maybe not significant. But when we combine together, because the treatment satisfaction is highly related to the angular severity.
Right.
Yeah, so this is the reason we need to consider that.
I see.
Yeah.
I see.
The compared to others, see here, this is like a very simple. We just need to add one. Okay, for the model, the left side usually we only have one variable, but here we could have like as many variables as possible as outcomes. For the outcome, we only need to get one line, MANOVA H equals or. They will provide us all of the results, separate ANOVA and MANOVA, once and for all. Like for others, like R, we need to use the different R command line. Yeah, so this is the reason we need to consider the MANOVA.
I see. Thank you.
Okay.
Any other questions for Zugui? All right, no other questions. So thank you so much, Zugui.
Claudine, I have a question. Claudine, this is Leela.
Yes, go ahead, Leela.
Zugui, you talked about using structure equation modeling, right? SEM,
yes.
Which is the problem I have with it is I've tried. I think you have to have very solid theory because I could never get a good fit, and I don't think there are that many theories in medical sciences. I mean, in social science related to, like, for example, in diabetes. And if I were to, you have to predict the relationship ahead of time, and then the data has to fit. But it's very difficult to do that. And I was wondering, what do you do when the model doesn't fit? Because when you try to adjust one, then everything gets messed up. So what do you do? I think you've used it, haven't you?
Yeah, this is tricky to provide code. Yeah, so first you need to like specify what kind of relationship.
Correct.
And yeah, so what relationship you need to specify. And okay, so specifically, we need to, yeah, so like basically for this structure, you need to have clear ideas, and then clinical need to explain the relationship, and then specify the code.
Yeah, and then when it doesn't fit, what do you do? Do you move things around, or what do you do? I just gave up and I got out of it.
Oh, okay, yeah. Basically, usually I try the different structure, and then yeah,
okay.
I know what you mean, and then for this maybe your CFI or TLI is not good enough.
Yeah, I mean, I was getting a significant difference, and you don't want a significant difference. So.
Yeah. Okay. Yeah. So this structure is visualize the relationship, and then based upon we will have this code. This code we can use M+, and often, and now R provides some package is called Harvard package for us to run analysis.
Okay. Thank you.
Sure.
Thank you, Leela. All right, any other question? All right. Well, thank you so much, Zugui. And